Okay, thanks for showing up for the second talk. So I'll talk about this magic angle graphene, which you already heard quite a bit about in some of the other talks. And I want to think about correlation effects and superconductivity. But it turns out really to understand this better, you need to understand the single particle physics of the bands in magic angle graphene, in particular the topology. At least that's what we think. So a lot of the talk today will be concerned with understanding the topology of this one particle problem, but you'll see it's very important to understand the correlation effects, maybe the superconductivity as well, we don't know. So let's see how far I get, but I suspect I may have to talk, spread some of the material of this topic to the next lecture as well. Okay, so I prefer to go slow and, feel free to ask questions during the talk. I know it's a big auditorium. I'll try to repeat the questions so it can be recorded. But yeah, feel free to stop me. Okay, so before we get to twisted bilayer graphene, let me remind you a couple of important things about graphene that I'm going to repeatedly use. Just this two-dimensional carbon sheet, but we're going to label the two atoms in the sublattice A and B. And of course, if you work with the nearest neighbor hopping Hamiltonian, a good approximation of the band structure, which looks like this. And there are these Dirac points. Stoichiometry, the usual electronic filling, gives you a chemical potential at the Dirac points. And the hopping Hamiltonian looks like this. There's a Pauli matrix, sigma. Sigma z refers to the A and B sublattices, plus and minus 1. And of course, it's entirely off diagonal in the Pauli matrices, sigma x and sigma y components for the nearest neighbor hopping. Okay? So you can think of this as some unit vector, and because it's in the plane, you get vortices, and the location of the vortices are the Dirac points where the two bands touch. Okay, and they touch at these 2 points, k and minus k, and these are the two valleys. That's a term I'll keep using. The two valleys of graphene. Okay, so low energy physics essentially is a pair of Dirac points. There are two flavors, whether you're at plus k or minus k. Also have spin, so all in all 4 flavors of fermions. Okay, so how do you perturb this problem? Actually, before I get there, let me make one more comment. The fact that you don't have this sigma z component in the Hamiltonian means that you have this chiral symmetry or sublattice symmetry. Usually when you have a symmetry, you have a matrix that commutes with the Hamiltonian. Okay, but here we have a matrix that anti-commutes with the Hamiltonian. Take sigma z, it anti-commutes with these two components. And so it's sometimes called a symmetry, but it really has this property that you only hop between opposite sublattices. Okay, so you'll see this is kind of important for a lot of our discussion. It appears right here in the tight binding model for graphene. Okay, and it would be spoiled if you have, for example, a potential on the sides, let's say a different potential on the A and B sublattices. That's a potential proportional to sigma z. It would spoil this chiral symmetry. Okay, so now we're going to think about this problem. You have a sheet of graphene, you have another sheet, and then you twist one with relative to the other. This is at a fairly large angle, just to show that you have this Moire pattern that appears, this lattice on top of the lattice. Okay? And of course, we're talking about much smaller angles. We're going to be interested in a twist of 1 degree. Sorry, this is just to show the Moire lattice. It forms a triangular lattice in this particular case because you start with the triangular lattice, Bravais lattice for the honeycomb system. And so now let's go to our more realistic kind of angle, 1 degree. So the lattice has been shrunk so that you can actually see this in the same size. This animation is due to Leon Balens. And you, of course, now have a much larger period for this Moire superlattice, about 13 nanometers. And we're really talking about electrons propagating in this superlattice and the effect the superlattice has on them. Okay, so before we go talking about how this reconstructs the band structure of graphene, let me remind you about the Dirac points of graphene. They're rather robust. If you want to remove them, you need to do one of 3 things. You either need to add a staggered potential, like, for example, if the A and B sublattices have different potentials, that's called a staggered potential, and that will introduce a mass term, which will open a gap and give a mass to these massless Dirac fermions. So for example, instead of carbon on every site, if you had different elements, say boron and nitrogen, boron nitride, that naturally gives you a staggered potential. And we'll see later that people can actually bring a substrate of boron nitride on top of this carbon sheet and effectively impress this kind of a staggered potential. The other way to break, get rid of this Dirac point is to break time reversal symmetry. So there's a second neighbor imaginary hopping term that you can add. Again, that breaks chiral symmetry. It connects things with the same sublattice. Can end up giving you a gap. That's called the Haldane term. Or you can break the rotation symmetry of the graphene. The rotation symmetry is what pins the Dirac points at these special locations in the Brillouin zone. You can break rotation symmetry. They move off those high symmetry points, and then they can eventually annihilate when they get to the center of the Brillouin zone, for example. That needs a finite strength. Either of these, even an infinitesimal breaking of time reversal or inversion symmetry will immediately gap out Dirac points. Okay, so there's a qualitatively distinct aspect to this third perturbation. Okay, so these Dirac points are quite robust. So we want to think about this problem, this bilayer problem, in terms of perturbing this Dirac points. Okay, so in each layer you have one of these Dirac points at the K point. Now we have the second layer, which is slightly twisted relative to the first one. So the Brillouin zone is twisted as well. That gives you a pair of Dirac points. And you can think of that pair as forming a new Brillouin zone. That really defines the new Brillouin zone of this Moire lattice. In fact, that will give you the right size for this Brillouin zone. So they're sitting at the corners of this new Brillouin zone, one Dirac point from the top, one from the bottom valley, one from the bottom layer. And then you have the other valley, which gives you a similar pair of Dirac points. Okay, so it's kind of a doubling of the degrees of freedom. This is assuming that the two layers don't talk to each other. They're just giving rise to these Dirac points. So if you zoom in over here, you see this tiny Moire Brillouin zone, whose size is essentially the angle times the original size of the Brillouin zone. Okay, the linear size is scaled by the angle. That's why it's this tiny thing. And it has these two Dirac points. Okay, so now we want to ask what is the special angle? This could happen for any angle. Why do we have the special angle where a lot of the interesting physics happens? And for that, you need to do a simple back of the envelope calculation to see when the coupling between the two layers becomes important. Okay, what is the scale? What is the angle at which the coupling between the layers becomes important? So there's this one energy scale, which is this is of the original graphene. It's kind of the bandwidth of the original graphene. You just take the velocity of graphene Dirac point multiplied by the largest wave vector in the Brillouin zone. That gives you an energy scale. That's one energy scale. And now, of course, if you have a pair of these and you twist it, the relevant separation over here is not the entire Brillouin zone. It's just scaled by the angle. So the same energy scale gets multiplied by the angle. Okay, so that is really, if you like, the energy difference between the Dirac cone and where these bands will meet if you just extrapolate them. Okay, so that's one energy scale. The kinetic energy, yeah.
Earlier, we defined that 2 kd sine theta by 2 under the assumption that the two layers don't interact.
Right.
Right now, I'm assuming that we are continuing from there only, calculating for when the...
Yeah. So we're going to compare two things. One is the dispersion over here compared to the coupling between the layers. And so the coupling strength between the layers is about this energy scale. So when this energy scale is roughly comparable to this splitting over here, so when these bands cross, you'll get a gap, and the size of the gap is roughly set by this energy scale. And when that gap is significant compared to this energy scale over here, you can imagine flattening the bands. But you push away the states, and it comes down somewhere over here. So this is like a back of the envelope estimate. Of course, if you really want to do it, you have to keep them all together and kind of solve some equation to figure out what happens. In fact, it's not obvious you'll get a flat band. And there are models where you can change parameters a little bit. You can still make this argument, but you don't get a flat band. Okay, so this is sort of a necessary condition. If you don't satisfy this, if this angle is bigger than what this condition gives you, then it's hard to imagine how a smaller scale like this will end up giving you a flat band. Okay, so it's a necessary but not sufficient condition to get a flat band. Okay, so anyway, you use this estimate and you solve for theta, you get about 1 degree. That's when the coupling between the layers begins to be of the same order as the kinetic energy of the graphene sheets. Okay, so just to give you a picture for what will happen, I'll actually show you the band structure showing up like this. So you get this mini band, that is the electrons moving around in this periodic potential. You see these bands, there's kind of a pair of them. These are the two different valleys. Okay, so the dispersion is not exactly the same. They're related by symmetry. So there are two of these valleys, and you see that there are actually two of these bands. So it's a bit like graphene. There are two bands that touch at a certain point in this Moire-Brillouin zone. Okay, so all in all, we have 4 bands over here. And if you account for spin degeneracy, there's an additional factor of 2. So if I go from completely empty to completely full, I need to add 8 electrons. Okay, 2 spins, 2 valleys, 2 of these bands, 8 electrons per Moire unit cell. Okay, so that is full to empty. That is the filling we're going to talk about. So if you have a band insulator, when you completely empty it and you completely fill it, that's no surprise. They see that. What is somewhat surprising is that even at fractional fillings, they see band insulators. And for that, we'll have to invoke electron interaction, which is quite reasonable because estimates of this bandwidth, they are about 10 millivolts. It's smaller than the gap to the other bands. So you can think of this roughly as an isolated system. And the interaction scale is about a factor of 3 larger than this bandwidth, and comparable to these gaps. So to the first approximation, we can think of this as an isolated system with some interaction strength V, and try to figure out what is happening over here. So this is a very crude estimate. So imagine that you have electrons that are separated. One electron is on one Moire lattice side, the other one is at the other side. What is the Coulomb interaction given the dielectric constants that people know for the substrate? So you multiply this by 60, that's the angle in radians, inverse radians. So you multiply this by 60, you should get a U that is roughly like what you expect for Coop rates. And in fact, it is, right? It's about 2 electron volts. Yeah, so that is kind of the problem. And so the interaction dominates over this bandwidth, or it could, if your bands actually get this narrow. So the question is, why do the bands get this narrow? And what do you expect in that particular case? Okay, so let me just briefly review the experiments on this material. So this is the case of this bilayer graphene that we just talked about, where you have the twisted at the magic angle, where in the first set of experiments, people saw these correlated insulating states and the superconductors next to them. It was very quickly verified in another very nice experiment, and there are a bunch of experiments now. I'll show this in a little more detail. So this is the system that we'll be interested in. There are also a bunch of other systems that you can call Moire Materials. Instead of being just bilayer graphene, here's one that was looked at very early on. It's ABC trilayer graphene. So 3 sheets of graphene stacked in a particular arrangement on a substrate. There's a boron nitride substrate which has a slightly different lattice constant. Okay, so that the mismatch in the lattice constants between graphene and the boron nitride ends up giving a superlattice, which is like this Moire superlattice. And by applying, there's an additional knob over here. They apply a vertical electric field. And if you do all of this, you again get physics similar to this. You see this Mott insulating phase. You see superconductors as well, but that requires a little bit of coaxing. It's not as obvious as in this particular system. There's also a bilayer on bilayer system like this one over here. You take a bilayer graphene that's not twisted, put it on another bilayer system, and the two are twisted relative to one another. And again, with this applied electric field, you can get insulators, claim of superconductivity as well. But it's not very clear. It's again not as clear as in this particular case. And then finally, there's this other material, monolayer graphene on monolayer graphene, so like this, but with an HPN substrate. And in that particular case, there's again I've kind of tried to make a distinction in this set of examples and this one, and really the distinction is one of symmetry. Okay, so this is this has a C2 symmetry. There's a rotation by 180 degrees that's present, which is not present in all of these systems. Okay, so
this one, there was no substrate?
That's a good question. In this one?
Huh.
Yeah, so there is a substrate. There is an HPN substrate. It turns out, unlike over here, the potential from the substrate is much weaker compared to the potential from this, from these, from the bilayer potential. There are two effects. One is you have this bilayer of carbon, and then you have this HPN substrate. And there's a question of whether you align that substrate to this carbon sheet. So it turns out when you align the HPN substrate carefully to the carbon sheets, there's a big effect on the substrate. I'll talk about that later. But if not,
what's the difference between that and the third one?
Yeah, that's right. Yeah,
same.
yeah, it's the same system, but this is aligned. So the substrate is important. That's right. That's a good point. Yeah. Yeah. So you have the cubic band touching, and then this substrate potential breaks that up into mini bands. Typically, they will overlap, but then if you allow for a vertical electric field, you can separate them out. So you need this additional knob. You need both the vertical electric field and the substrate to get the correlated physics. And so here we do not have this C2 rotation symmetry. If I rotate by 180 degrees, you get a different system, right? The thing that was pointing down now was pointing up before. Okay, so so we're going to include the C2 symmetry for the most part. We'll talk a little bit about this case because it kind of gives you a more interesting problem, and maybe there's some differences arising from this symmetry. Okay, so to be talk about the experiment in slightly more detail, there's we said we had this kind of band structure for these nearly flat bands. So there's charge neutrality when you're midway through this band structure. That's like being at this particular carrier density. Let's call that 0. That's traditionally called 0. And you think of doping it with electrons or with holes, either plus 4 electrons or minus 4 electrons on each Moire unit cell. Okay, that's a total of 8. We did this count before. So imagine going from charge neutrality up to the top of this band. That's like going from this charge neutrality point to this point over here, where you get an insulating phase. So this is the conductance. Conductance drops to 0 over here because you completely fill this band. Okay, so that's no surprise that you get an insulator over here. Similarly, you get an insulator over here if you completely empty the band. I haven't shown that in detail. But what they saw in this particular, in the first experiment a year and a half ago, is even if you go halfway, so now you are at filling of 2 electrons per Moire superlattice cell, you end up getting an insulating phase. And similarly over here, you have a total of 6 electrons per Moire unit cell. You have an insulating phase. So that was the first surprise, that there's some correlation-induced insulators. They called it a Mott insulator, but essentially it's something that's induced by electron interactions. And now you can zoom in over here. That's this picture over here. You have this thing they call a Mott insulator. You slightly dope it, and you end up seeing superconductivity on either side, although this one appears to be stronger. The one on the further away from charge neutrality appears to be stronger. So that was the situation in the first set of experiments. There were only 2 correlated insulators at -2 and +2. There was a dip at charge neutrality, but this did not quite seem to be insulating. And there was a lot of information extracted about the gaps and what happens under a magnetic field and so on and so forth that I won't try to review. Yeah. Right.
Or is there
Yeah, so the resistance rising with decreasing temperature could be from a gap. I mean, it could just be activation. Yeah, yeah. But from the band structure, you don't expect to see this insulating phase. So if you had just a non-interacting problem, you do not expect. Also, if you look at larger angles, so like 2 degrees, where you expect this bandwidth to be larger, there's a nice experiment by Pablo where they see some of the other features like these band insulators over here dip at charge neutrality, but they do not see this insulating phase. So it's consistent with the fact that interactions end up giving you that to you. There's another check on that, which I'll just mention in a minute. So anyway, this was the original kind of observation. But then, of course, other people started looking at this more carefully. So there's this group in Barcelona who apparently have the most uniform samples. And when they look at this, look at their samples, they see for example, insulator even at charge neutrality. Sometimes they see an insulator at filling of 3 electrons per Moire unit cell, and they have, of course, the 2. N equal to 2 and n equal to minus 2 is certainly there. And they also see superconductivity pretty much everywhere where the insulator is absent. Maybe not over here, but. So there's some question exactly about what this phase diagram looks like. But if you believe that this is somehow the pristine sample, you also have a gap at charge neutrality, and you have these other superconducting regions. And then there's a more recent experiment. So very hard to keep up with this field because every month there's a new paper which kind of alters the picture in some important way. And I think Eresberg will talk also about some new experiments, which actually I've not had time to read. It came out like a week back, and it's kind of very interesting new results. But here's another experiment that came out a few weeks back, where this group figured out that they have an extra knob that they can tune, which is the distance to the gates. Okay, this is kind of the sandwich they make: 2 layers of graphene, this HPN substrate, and then these top and bottom gates. And depending on the thickness of the substrate, you get less or more screening. The thicker the substrate is, the less screening that you have because the gate is further away. So in a way, that's a way to control interactions. And what they discovered is they have very thin HPN samples. So in some sense, their interactions should be thought of as being somewhat weaker than the MIT group interactions. And here, this is a device which has a very close gate. And now, some of these correlated insulators go away. For example, this n equal to 2 insulator is gone. The charge neutrality insulator is still there for them. The charge neutrality insulator is always the strongest insulator. Yeah, but this is consistent again with the fact that maybe these are correlation-induced insulators. You tune down the interaction, they go away. Yeah, but they still see superconductivity. So the exact connection between superconductivity and the insulating phases, which were very obvious in the initial experiment, they don't seem to be that clear when you go to these devices with weaker interaction strengths. Okay, so that's still a bit of a mystery. The distance to this gate, the thickness of the substrate, I think this is 12 nanometers. This is, and that's, yeah. Of course, you do many other things as well. But one of the things you do is to change the interaction strength. Somehow this should be more strongly interacting than that one. Okay, so that's some sample of the experiments. So if you think of this analogous to cuprates, for cuprates we also had an insulator, and then you doped it, you got a superconductor. And in the years since then, there's been a lot of discussion. But we know, for example, the insulator is antiferromagnetically ordered. Maybe that's not the whole story about the insulator, but a sharp question that you can answer at 0 temperature: what does characterize the insulator? It has antiferromagnetic order. We know the superconductor is a D-wave superconductor in the cuprates. So we'd like to have at least a similar level of understanding for this system. Some obvious question: what is the nature of the insulating state? If it's ordered, what is the nature of the order parameter? Superconductor, what is the nature of the pairing symmetry? At least these are like unambiguous questions, unlike questions like what is the mechanism of superconductivity, which may not have very clear-cut answer. Yeah, so that's kind of the program, for theory and experiment, I guess, at least to my mind. The first thing is to kind of establish those obvious kind of questions. Yeah, so let me now kind of take a step back and tell you, kind of review the theory of these bands. of these nearly flat bands. Again, of course, a very important consideration are the symmetries of the problem. So this is a picture at rather large angle. You've taken these two sheets and twisted them around a common hexagon center. And you can see this pattern has got a C6 symmetry. You also have a symmetry where you flip the whole sheet around this axis by 180 degrees. You can think of it as like a mirror, but actually you also exchange the top and bottom layer. It's really a rotation around this line. So that gives you like a D6 symmetry group. Okay, you also have, of course, the time reversal symmetry that's kind of assumed. But this is really for a fairly large angle. We're going to be interested in much smaller angles. What happens at large angles is you can think of two different sheets. For example, you can think of taking the sheet and shifting all the atoms over, make it look like this. Okay, so this is a pair of sheets where you twist it around a common site rather than a common plaquette center. And now the symmetry is lower. It looks like a C3 symmetry. You don't have 180-degree rotation symmetry. And actually, if you twist it around some other random point, neither the plaquette nor the site, you would have no such rotation symmetry. Okay, but this is a bit misleading because when you go to small angles, regardless of how you twist this, you're going to have an emergent C6 symmetry. Okay, so you can draw some pictures of these things with twisted around different points. You'll be unable to tell from the pictures, whether it was this kind of configuration or this one, or some third one where you were not aligning anything. In the limit of small angle, these distinctions are irrelevant, and you have this, pretty much always have this emergent C6 symmetry, as long as you don't worry about the substrate. You also effectively have a valley U1 symmetry. There's no scattering between the opposite valleys because the length scale over here is so much larger than the atomic length scale. So if an electron starts in one valley, at least at the single particle level, it doesn't scatter to the other valley. Yeah, it's also, sometimes when you think about these, there's some quasi-crystal kind of physics. Maybe these different Moire islands are not exactly the same. If you look carefully, they may be different. But again, the limit of small angles, this is not important, whether it's commensurate or incommensurate. Those are really things that you realize when you scatter many, many times, and you can check the commensuration between this large scale and the very short scale of the atomic lattice. Extremely unlikely, so this is also kind of irrelevant. Okay, so really the emergent symmetries are this D6 and this valley U1, along with time reversal. Okay, so a simple model for this, the band structure was given by many people, including this Bistreiser-McDonald, where they said that there are, the components are very simple. You have these two layers. In each layer, you have a Dirac theory. That's a sigma dot grad kind of theory. It's slightly rotated. This rotation is not really important because you've got to keep track of the fact that these layers are rotated relative to one another. And then you have essentially the coupling between the layers is really introduced through hopping. Okay, the layer sees the other one because it drops into the other one and moves there for a while and then comes back up. Okay, so it's really this matrix that determines the coupling between the layers. Okay, so this is a space of up and down layers, but each of these matrices over here are 2x2 matrices referring to the AB sublattice. Okay, so the hopping, for example, is hopping from the top to the bottom in the A to A subregion, A to B, B to B, and A to B. Okay, so you have essentially, it turns out there are two parameters over here. I'll have a picture very soon to talk about what this AA and AB means. But there are these two parameters, the hopping strengths, and you can normalize them by the kinetic energy. That's what we did before. Right? So it gives you two dimensionless parameters. And in this Bistreiser-McDonald model, these two hoppings are just set equal to one another. Okay, so there's only one dimensionless parameter, which is controlled by the angle. Okay, so you can say the angle is effectively the dimensionless parameter in the problem. And when this angle this effective thing is of order 1, is when you get this magic angle physics. Okay, this turns out to be 0.6 in this language. Okay, so this parameter is going to be inverse of the angle. So you'll have to keep track of that when you. And when you tune it to this particular angle, you get this very, very flat band. You also get these other bands in this model. But that's why they call this the magic angle. It turns out if you look carefully at this problem. It's not quite true that the hopping between this, the AA and the AB regions are the same. And the reason arises from this lattice relaxation. So this is what I meant by the AA region. If you look at the two layers on top of one another, the sides are almost on top of each other. That's called the AA region. In fact, in the 1 degree case, they'll kind of occlude each other because they're almost on top of each other. The AB region, on the other hand, are like these regions over here. Okay, so here one side is on top of the other one, but the other is in the center of the plaquettes. It looks like Bernal stack graphene. That's actually the mechanically stable configuration, and the system tries to maximize that. Okay, that's really why the hopping strength for the AB ends up becoming bigger if you make a more careful calculation compared to the hopping strength between the AA regions. Okay, the sheets get a little closer, they expand, they all kind of reduce W0 and increase W1. Okay, so the more realistic model, actually you go from one where the two are equal to one where this W0 is only 75% of the W1. And that turns out to be very important in this problem because here you have this very flat band, but the other bands are coming very close to this flat band. They even touch it. Okay, but once you include this effect, the main effect is it doesn't actually change the dispersion very much, but it pushes away these other bands. And in order to make contact with the experiments where they see a fairly large gap over here, this is the simplest way to kind of account for that. Okay, so this lattice relaxation is important in getting the final picture. Okay, so but for our purposes, what we're going to do is, this seems like a good idea. We thought, why not push this all the way and simply set this W0 equal to 0. Okay, so what if I just shut off the hopping between the AA regions and only keep the hopping between the A and B regions of this graphene bilayer? And in that case, what happens, not only do you get this well-separated band, you also get this chiral symmetry. Okay, so once you shut off this AA hopping, everything in this problem only hops between the A and B sublattices. Okay, so you have this, this chiral symmetry we talked about before. There's a fixed matrix that anti-commutes with my Hamiltonian, which is really the sublattice matrix. And this ends up giving this model some very nice properties. And we think that's really the correct starting point to think about this twisted bilayer problem. And in fact, we'll be able to figure out an analytic solution for why you get the flat bands, really some form of the wave function of the flat bands. And everything really simplifies in this particular limit. It's a little bit like the lowest Landau level limit of some particle in a magnetic field. All the wave functions are very simple. And then if you want to get back to reality, you have to add some other perturbations. So the philosophy we'll take is to start from this limit and then add other perturbations in order to get back to the actual system. Okay, so one of the things that's very nice about this model is you can show that it has exactly flat bands, and kind of argue that for you in a second. So once you switch off this AA coupling, we said that everything appears in hopping between the A and B sublattices. And so if I write it in this particular basis, I only have off-diagonal elements. And if you go and look at what these off-diagonal elements are, it looks like this. There's a derivative operator, and then there is this interlayer hopping term. So this is written in the layer space. I kind of flip the indices around. Okay, so this derivative is just the anti-holomorphic derivative, x plus I y. And there's, of course, the complex conjugate of that in the other block. Okay. So you'll see that this holomorphicity that you're used to from Landau level physics will make an appearance over here as well. And of course, we have this one dimensionless parameter that's going to be sitting over there, which we are going to imagine tuning to see what happens to this band structure. Okay, so it's pointed out some time back that you can think of this problem as electrons or some fermions moving in a non-abelian SU2 gauge field, non-abelian vector potential, static vector potential, of course. This vector potential really has the layer as the Pauli matrix over here. It's really this term over here. It has an x and y component, and it's non-abelian because it has both the tau x and the tau y components. And so it turns out, for reasons we don't quite understand, it's extremely important that this vector potential be non-abelian. Okay, so you keep everything the same. You arrange for this potential so that this term cancels out, let's say, so it has only one component, you don't get the flat band. You need a little bit of this to get the flat band. Yeah, so that's something we don't, it's kind of hard to keep track of why something should be non-abelian, but it turns out to be important, yeah. So this is not quite a magnetic field. I mean, we have to talk about it in this particular form. In this particular form, if I have only real hopping between the layers, we just did the calculation, we find there's no magic angle. Things always have some dispersion. You put in a bit of this, then you begin to get these flat bands. Of course, in the real problem, these two are of roughly the same strength. So it's deep inside the non-abelian kind of regime. But you can always play with this just as a toy model, and it turns out to be important. Okay, so now let's just take this model with the kind of realistic hopping on at least on the AB part of the regions, and tune the angle. Okay, and of course this alpha is like the inverse of the angle. So I'm starting in a regime where the angle is very big. I have some reconstruction. I have these kind of bands, and then I tune that towards the magic angle. And let's see what happens. You see that these things separate out. They're getting more and more flat. And when you hit this magic angle, it becomes extremely flat. And then you continue, you go to even smaller angles. These things begin to disperse, but then there is some kind of a recurrence. You go to alpha of about 2, which is 4 times smaller than the original magic angle. Again, you get this flat band. And so on. There's actually an infinite sequence in this model where you have these well-separated bands that become completely flat at particular values of this of angle. Yeah, so we'd like to understand this better. One thing we did saw when we first saw this was it looks numerically very flat, but is it perfectly flat? Is it really zero dispersion? And we were able to prove that it's really zero dispersion in this Chiral model. Okay, so let me tell you what the argument for that is. That's a good question. I'll talk a little bit about that. Yeah. Yeah, so the thing is, to go to the experiment, you've got to put back the reconstruction, the finite W0. Somehow it turns out the first magic angle is extremely resistant to that. Basically, nothing changes to first approximation, but the others are quite sensitive. But that's not quite the whole story, because for the others, they're at smaller angles. So the relaxation is actually much larger for them. So you have two competing effects. They're more sensitive, but the W0 is actually much smaller. The small angle, things reconstruct a lot. You can get a lot of advantage. So that competition, we don't know which one wins. Does the sensitivity win, or does the smaller alpha? Yeah. That's a good question. So it's not directly measured. So people do like an ab initio calculation of the structure. What is the best structure for a particular angle? And given that best structure, they calculate the the effective parameters. And then you can go back and see what the gaps you predict are. But it would be nice if somebody could directly measure that, the coupling. I don't know how to do it. Good question. Yeah. Yes, yeah, I'll get to that. I'll talk about that. So that report of ferromagnetism is very important to have an aligned HPN substrate. So that's the story where you break the C2 symmetry, and yeah, we'll talk about that. So, yeah, that's what I would think. But usually when I say that, 2 days later, there's a paper with photo emission. So I hope someday will do that. Happened. Okay, so just bear with me for a couple of slides where, or go to sleep if you find it boring. But I want to tell you the analytic argument for why this has this exactly zero energy states. Okay, so it's a very nice argument, I think. So we are looking for a situation where these bands, the bands near near neutrality, become completely flat. It turns out in this chiral model, so basically we're looking for zero modes, zero energy states, which is, as you know, typically much easier than solving for some other eigenstate. Yeah, and so it turns out that if you're at certain crystal momenta, this k points, you're guaranteed to have a zero mode. Okay, these are essentially the Dirac points that came from the original, from the layers. The chiral symmetry essentially guarantees for you that these are not going to go anywhere. They're going to stay there. Okay, the challenge is to show that not just those points in the Brillouin zone, but everything else is zero energy. And generally, this does not happen. If you're at some angle, random angle does not happen. Somehow, by tuning a parameter, you should find that there's a zero mode solution for every momentum. Okay, so here's the equation that we want to solve. We want to solve this d times psi is 0. Essentially, these psi's are this is the entirely on one sublattice. Okay, so we only took half of this part of this equation. So recall, this is the thing we need to solve. 8 psi is some eigenstate. But if you're looking for zero mode, it simplifies. You just need this block to annihilate the vector, 2 by 2 block. So you already specialized to a particular sublattice. We are asking for the up and down layer index 2-component wave function to give you a zero mode. Okay, so that's this 2-component equation. You want it to be 0. And if you're at the k point, you're automatically guaranteed a solution. The question is, can you get it at some other crystal momentum? It looks like you should be able to get a zero mode at any crystal momentum. And the reason is that if you give me one solution like this, I can imagine multiplying it by any analytic function and generate another zero mode. Okay, so you can see if this is a solution, this product is not going to do anything because this derivative, that's the only thing that could care about the overall scalar in front. The derivative goes right through because it's a d bar, doesn't act on the z's. Okay, so this should be also a zero mode solution. It looks like you can always get these, you get a multiplicity of the zero mode solutions. But of course, the thing that's important is you have to have the right boundary conditions. You need that this has a particular crystal momentum. And in general, you cannot do that with an analytic function. You can't write an analytic function. So there's some trade-offs. Okay, so let's see what that trade-off is. So you want this analytic function that has the right, which should be doubly periodic, essentially. Right? So there are analytic functions like that. They're ratios of theta functions. Okay, so you take the right ratio of a theta function, you can get the right crystal momentum. But the problem is that this thing in the denominator is going to end up giving you a pole, and this is going to give you a non-normalizable wave function. Okay, so we'll see how to fix that, and the solution to that will be picking the right angle. Okay, those two problems will kind of solve each other. Okay, but very quickly, let me give you a reminder of these theta functions. So since I'm giving this at TFR institution, I should give you this reference. This is lectures on theta functions which were given at the Tata Institute, right? Tata lectures on theta, very nice reference. So some of the identities that you can find there, there's this theta 1 that you can define. So there are these two indices, you fix them, gives you this theta 1. I'll talk about everything in terms of this theta 1 function. So this is an infinite series representation of the theta function. Okay, so you have a sum on these integers, and you have this this particular form. Maybe it's not very illuminating, but you would have seen things like this. It kind of looks like a Gaussian, right? So it's if you like some kind of Gaussian which has been made periodic by shifting it through the crystal lattice. Yeah, and important thing that I need to say is that these theta functions have roots, okay, and the roots of this theta function are at these positions in the complex plane. Okay, so because they have roots, this particular solution, although it has the right boundary condition properties, it is not normalizable anymore unless this wave function can step in and fix the problem. Okay, so how do you get this to be a valid wave function? You can do that if the 0 over here cancels against the 0 of this wave function over here. You need that the spinor wave function over here should completely vanish at the same point that this wave function over here vanishes. So you should be able to arrange that. Okay, so it turns out, miraculously in this problem, this spinor wave function, although it's two complex numbers, I give you two complex numbers, you can't set them equal to 0 by tuning one parameter, by tuning the angle. So it turns out there are points in the unit cell where they automatically vanish, at least one component vanishes, so you're just left with tuning one complex number to 0. The overall phase is not important. One real number is 0. So in terms of parameters, you have enough parameters to tune this to 0 by changing the angle. As soon as you get a 0 in this wave function, you're allowed to have this denominator, and you can construct solutions for the entire band, which are 0 modes. Okay, so given this condition, you can get a zero energy band, and the wave functions, the flat band wave functions, look like this. Okay, so maybe it's not very illuminating, it's some ratio of theta functions. But one thing that's very nice, which we used in a recent paper, is that this is actually an analytic function of K. Okay, so if you look at the wave functions, the periodic wave function is a function of crystal momentum, Kx plus Iky. It only depends on Kx plus Iky. It doesn't depend on Kx minus Iky. Okay, so I'll mention that later. But it really has a form that's very reminiscent of Landau levels. So just to give you a comparison, this is the wave functions that we are talking about. If I look at all the wave functions in this flat band, I can think of them as having this overall factor times some analytic function of z. And Landau levels, for example, on a torus, have this particular form. There's a different factor. This factor is slightly different, multiplying this function of z. Okay, but there's a very close relation. And in fact, this particular band, which is resolved by sublattice, so I picked one sublattice of this flat band, actually has a Chern number. Okay, so sorry, yeah. So it's like we have this pair of flat bands. I go to a different basis. When there's no dispersion, I can go to a different basis where the bands live entirely on the A and the B sublattice, and one of them has Chern number 1, the other one has Chern number -1. Okay, this is at one particular value. Okay, so this is really what the solution tells you when you're at the magic angle in this chiral limit. You get a pair of opposite Chern number bands, and they live entirely on one sublattice of the graphene atoms. Okay, so it may remind you of a graphene and a magnetic field. If you take graphene and a magnetic field, the wave functions live entirely on the A or the B sublattice, depending on which valley they're in. Here it's slightly different. Even if I pick a valley, there are two bands. One of them lives entirely on the A, one of them lives entirely on the B, and they have opposite Chern number. Okay, so this is in this very important to be in this chiral limit where everything's completely flat. I have a choice of whether to take the natural band basis or this sublattice basis. And I have no dispersion, it's my choice, and I can go to this basis where they have Chern number. Yeah. Yeah, sorry. So omega is the cube root of unity. So if you have a triangular lattice, if I want to represent that in terms of complex coordinates, you would use that to represent the two vectors. So tau is a general complex number. So if I didn't tell you it had triangular lattice symmetry, you have a torus. It's represented by unit length in one direction and a complex number tau in the other direction. That defines the torus for you. So those theta functions are defined for a general complex number tau. And tau is set equal to omega for the triangular lattice. Yeah, thanks. Yeah. Well, you can always go to this basis, but it won't diagonalize the kinetic energy in general. Yeah. But if you're at the flat band point, there is no kinetic energy. So this is an eigenbasis as well. You'll have to keep the kinetic energy. But somehow it turns out this basis is the right one to think about. That's what we have found after some long and, yeah. It turns out this is the right basis to think about. Just like, if I gave you Landau level, this is very much like a Landau level problem. Although there's no magnetic field applied. You think, why should I use this basis? But somehow this way of thinking about it gives you the simple way to understand a lot of the energetics. For example, you can ask what happens when I add this HBN potential substrate. Okay, and what that does is gives you a different potential on the A and B sublattices. And what it will do in this setting is it will separate out these bands, it will pull one below the other. and you'll end up getting a band with a particular Chern number. And now in the opposite valley, everything is reversed, you get the band with the opposite Chern number, which makes sense because you didn't break time reversal. Yeah, but if you imagine that the interactions spontaneously pick one of the valleys and pick one of the spins, then you could imagine getting a spontaneous quantum Hall state, which has some particular Chern number when you break the symmetry between A and B. Other ways of thinking about this as well, yeah. Yes, yes, yeah. So this would be zero magnetic field, and interactions are important to spontaneously break time reversal. Of course, you can't get quantum Hall without breaking time reversal. Usually we do it explicitly by putting on a magnetic field, but this is a situation where you sort of generate magnetism. Spontaneously break time reversal. It's a little bit like this chromium-doped bismuth selenide. You have some chromium atoms, they break time reversal for you. You end up getting the spontaneous Chern insulator there. But there it's two components. Here it's all one component. Yes. Yeah, so you might think that because they don't match, there is some sort of mass term that prefers B over A in some region, and then later as you go along, you get the opposite thing. So they'll all cancel out. But it turns out that does not happen. It turns out even though they're not commensurate, you get a uniform value of this splitting. And then you get a superlattice on top of that. That is the effect of the mismatch. But it's not like it changes the sign of this mass term. The thing that will change the sign is if you rotate the substrate by 60 degrees or 180 degrees. That will switch the sign of this mass term. But that's not what's happening when you go from one region to another. It's not rotating. It's just getting displaced relative to the underlying lattice. Because it's really rotations that reverses the sign. The A and B sublattice of HPN, they are like different sites in the unit cell. They don't go into each other by displacements. Right. I have a picture of HPN. You can see. You can tell if there's a HPN that's aligned like this or aligned like that, even if they're not exactly in commensuration. So it's not, from symmetries you actually expect this, and people have calculated what the value of this splitting is, and it's actually quite large, it's like 30 millivolts. But you need alignment. I mean, if you don't align it, if it's different angle, then the effect is much smaller. Yeah, but actually, sorry, I saw somebody else, yeah. Maybe Sweta and then you, okay. Yeah. So there is some very close analog to that. Yeah, so I'll actually come to that in a second. So it's got to do the quantum geometry of this band. And because it's a Chern band, it essentially has that property. But you can ask how close is it to the Landau level. The Landau level not only has the topology of Chern number 1, it has some very uniform kind of representation of that Chern number. So here it is actually relatively uniform. That's what we are finding. So you can almost write down this non-commutation kind of algebra, this GMP algebra, for example, in this case. Yeah, presumably. I don't think we know exactly what it looks like, but roughly speaking, you take the answer for the Landau level and you substitute this factor with this one. That's roughly how things work. So for the K point, definitely there's an index theorem. Although I've not seen it written like that, it would be nice to find that. But the argument is very index theorem-like argument. But for the others, it's not clear to me that there is an index theorem kind of argument because it happens at a particular value of the parameter. Right? You would think index theorem, it would be independent of the value of that parameter. But maybe there's some way to introduce that parameter into the index theorem, I don't know. Yeah, it would be good to have something like that. Okay, so this idea of splitting the, splitting with HPN. So this is HPN, this is what HPN looks like, two different atoms in the NB sublattice. This idea of splitting it with an aligned HPN, so it's as somebody mentioned, David Goldhaber-Gordon and Andrea Young's group did it. And then you get these splittings, the bands are split. This is one valley, the other valley is chart number 1 and -1 with the spins included as well. And then you fill it, you just fill one of these bands, and then you have to make a choice. You have to pick a valley, you have to pick a particular Chern number over here and a particular spin. And then you find that the Hall conductance is quantized. This is the quantized value 1 and -1. And this is the classic, the plateaus of the Hall conductance 0, 1, or -1. And at those points, the longitudinal resistivity is 0, showing that you have some insulating phase. Okay, so this indeed works out. And we believe it's because of this aligned HPN substrate that breaks the C2 symmetry. Of course, one very natural question you could ask is, what if you have a fractional filling of these bands? Let's say you have this and then you fill it fractionally. Could you get a fractional Chern insulator? That would be very, very exciting, right? So we don't know yet, of course, experimentally, but let me just advertise this recent work. We try to look at the bands over here and see if they are favorable to forming a fractional Chern insulator state. We did it analytically. So you can try to see how close the bands are compared to a Landau level. Landau level we know gives you fractional quantum Hall if you partially fill it. So there are some metrics that you can check, some things that you can check. One of the things that people say is in these fractional Chern insulator literature, there's something known as a quantum metric of the flat band. So one component of the metric is the Berry curvature. That's the imaginary part of this quantum metric. The real part is this thing called the Fubini's 2D metric. And you want that to be uniform and you want it to have a particular form. That's ideal for this FCI. In fact, we find it has the right form. It has this fixed form. This is just the Berry curvature. This varies as a function of momentum in the crystal, in the unit cell, in the Brillouin zone, sorry. But the variation is quite small, at least for the chiral model. Okay, so the chiral model seems very ideal. Of course, the realistic model, you've got to introduce this W0. It's not as ideal. At least analytically, it's less clear. You'll get a fractional Chern insulator in that case. But it still doesn't change very much. Okay, there's still some hope that there will be a fractional Chern insulator. Also some numerical works that seem promising. So this would be something interesting for the future. One thing, let me mention, this form of this quantum metric completely arises from the other observation I mentioned, that those wave functions are analytic functions of K. That's all you need to know to get this form. Okay, so anyway, this is more like an advertisement. Yeah, so this is really what I wanted to get to, which is what happens when you have interaction effects. I mean, what I mentioned was actually an interaction effect because you picked a valley and a spin, but that's when you have the substrate being important. So suppose you have pristine magic angle graphene, what do interactions do? Do they give you, what kind of states do they give you? Okay, so in the remaining, I guess, 1 minute, let me just kind of make some philosophical comment. Yeah. Oh, in the experiment? Okay, you want me to go back there? Let me go back. Yeah. Yeah, it's hysteresis, yeah. There is something weird over here. So this is, you start out in -1, you put on a field, you need to coerce it with some field, you get to 0, coerce it a little more, you get to 1, and then you come back, you're still there in 1, but then you reverse the field. You don't quite get to 0 that well over here. Yeah. So that's what you expect from something that spontaneously breaks time reversal symmetry. Say again, oh, these little things. Yeah, I think it's, the thing is over here, there is dissipation. So our XX is, I'm assuming there is dissipation over here, right? 0 is probably for this one. So, in a dissipative state, you don't really expect to get plateaus, or you don't want to attribute anything big to that. It's probably domains that are flipping. You get stuck and then they flip maybe. Yeah, I think this quantization is correct, is accurate to 1 part in 1,000 at least, maybe more. It's reasonably good quantization. And I think the temperature scales are like few Kelvin, 4 or 5 Kelvin. So when they begin to 3 Kelvin or so, when they begin to see this good quantization. Yeah, it seems quite good. Okay, so I think I'm out of time. Yeah. Yeah. Yes, yeah, they are important. So let me just go back. In a very simple, in a ferromagnetism kind of way. So you have these 4 bands, and you're asked to fill one of them. Actually, you have 8 bands in all. There's 4, and each of them has spin degeneracy. And of course, there is a splitting because of this AB sublattice that picks these 2 bands up here and these 2 over here. Okay, so a priori, when I give you just a filling of 1, you would have gone and filled all 4 of these at some quarter filling. You would have gotten a metal. But it realizes it can lower its exchange energy by jumping into the same flavor for everything: spin polarized ferromagnet and valley polarized. That picks just one of them that has a unique Chern number, and that's the story for this state. Okay, so I guess I'm out of time. So let me stop over here. Next time, maybe I'll talk a little bit more about these interaction effects and how it fits into our paradigms of correlated electrons.
Thank you, Ashwin. Questions?
Ashwin, I would like to go back to your original argument on this coupling, how you get the idea of the, or estimate of the magic angle from the coupling between 2 layers.
Right.
I'm just trying to understand how generic it is. For example, suppose one reduces the coupling. I mean, one way of first you showed the gate on top, but then in that case, would you expect the coupling to happen, or the magic angle to happen at lower angle?
Okay, so when you say coupling, I mean the hopping between the layers.
That's right. So when I say sorry.
The gate changes the U, the interaction strength, but maybe not the hopping.
Right. So suppose you use a different separation between the 2 layers.
Yeah.
Then the hopping will be
different. One thing you could do is, which people have already done, is to put pressure. And then the sheets get a little bit closer, and then you get a different magic angle. In fact, you get a larger magic angle. And that seems to work out amazingly. They go to the new magic angle and they see the same physics. But all the scales have been now increased because the angle is larger, so they're all closer together.
Good question.
Hi. So I have 2 questions. One is that can you repeat the point of that incommensurability is like irrelevant for this low angle region for this thing?
Okay. I think I have a slide for that. My student Adrian made a slide for that. Okay, so these are actually they're not 1 degree. They're actually a somewhat larger angle, so it's even better. So some of these patterns have been twisted, keeping the plaquette on top of the other plaquette. Some of them have been twisted, keeping the site on top of the other site. And some have been picked with some random thing. The question is, can you identify the ones which don't have 6-fold rotation about the bright spots? Okay, let me tell you the answer. Obviously, it's these 2. Actually, I'm kidding. I can't tell. You can't tell, basically, right? Even at these angles. So if you can't tell, probably electron can't tell either. Right? So it's very hard at these small angles to tell which configuration you came up with. One way to think about it is if you twist it around some different point, you can go somewhere else in your structure and find the plaquettes aligning, almost aligning. And then it looks like something where you twisted around the plaquettes. So that's the reason it's not really meaningful to make these distinctions.
So these are all commensurate angles.
These are all.
Technically, in commensurate angle, you won't get a.
So what happens in the incommensurate thing is, if you look very carefully at these things with great detail, they are actually different from each other. But in the commensurate thing, they are exactly the same. But again, I could ask you the same question. Which of these are commensurate? Can you tell? And you can't. And at least in the simple model we used, it has a shift symmetry. This BN model, it has a symmetry that if you shift one layer relative to the other, nothing happens to your Hamiltonian, which is saying that it always has the C6 symmetry.
I think I'm jumping the gun, but is the interaction you are going to introduce a 2D long-range Coulomb interaction, or it's short-range?
It's going to be screened by the gates, but it's screened by the distance to the gates.
It's long-range on the scale of the Moire lattice?
Yeah, well, it depends on which, the ones I showed you, the thing where the gates were nearby, they are actually, some of them are actually quite close to this. Go back to that. Yeah, so the gate here is 7 nanometers. That's actually smaller than the separation between the Moire. But most of the other samples, this is like of the same order. Most of Pablo's samples, they're even further away. So there's a range. And we can adjust that, depending on what it is. That's not very essential, I think, the exact form of the interaction.
Do you have a sense why the superconducting domes shift as the distance of the gate changes?
Yeah, no idea. Actually, something very strange happens. If you look at this one, here the superconducting dome is on the right of this, what would have been the correlated insulator at filling -2. But in the original experiment by Pablo, he also had the superconducting dome, but the big one was on to the left, to the more hole doping side of this correlated insulator. So that thing kind of, went to the other side. And the correlated insulator went away. So I have no idea actually what's going on over here. So maybe, one thing people say, maybe phonons are important. If it's so widespread, it's there even without a very strong correlated insulator. There's also another experiment by Andrea Young where they see this physics. But it may be that you don't really need the correlated insulator there to get correlation physics, right? There's still interaction effects. So I think it's still open at this point.
Yeah, following on that, what happens to the phonons? Do you get a dispersionless phonon band?
No, you don't get the same band structure for the phonons. Completely different problem. You get some gapless phonons, but they're not flat. Yeah, but I don't know too much about the phonon band structure.
So if you have chiral symmetry breaking hoppings is AA hoppings, but your picture is you said is stable to that kind of hopping, right? So what gives that stability if it does?
I don't know, somehow that slide never came up. Let's see if I can find that slide. Yeah, sorry, I kind of lost. Here it is. Yeah, so this is what happens when you introduce this W0. So this is the chiral model. This is one thing you can look at is the band gap, how well isolated these states are from the others. And you see that this is the first magic angle. It kind of, the band gap goes down, and when you get to the BM model, it actually closes. But your realistic relaxation limit is somewhere over here. So it's sort of adiabatically connected to this chiral limit. So the wave function will change, but you think it may not change that much, or at least it's connected. You can take the physics over here and do perturbation theory and get here in some sense. But for the second magic angle, there's a lot of gap band closings and openings, so things change a lot if you take the same relaxation. Actually, relaxation is going to make it somewhat lower, so we don't know exactly there what's going to happen. The other thing I should mention, something we don't understand very well, we don't have a simple explanation, is that at least in the chiral model, you have this whole sequence of magic angles. If I look at this alpha, there's a separation of 3 halves. There's a period of 3 halves. That's the sequence. It's very accurately 3 halves, and it gets better closer to 3 halves. It's some asymptotic kind of formula. And there should be some simple way to understand that. But yeah, this is an open problem right now. We can see that numerically, but we don't have a simple understanding.
Experimentally say that there's a lot of sample dependence in this anomalously more than other systems they have studied. Is there any understanding from theory?
So one thing, the one thing people figured out, for example, the gate distance. Nobody had thought about gate distance before. And that seems to be something that in the Barcelona group, they have closer gates. So that's something you need to know, right?
Keep everything that you can think of that make different samples. Is it just hard to control that in a way that, because I heard that you have to make 50 samples to really see superconductivity.
It was reproduced very soon. So I think people have no trouble reproducing the superconductivity. But depending on who samples, I mean, of course, I'm like the theorist telling you about what they do in the experiment, right? But at least this Barcelona group, they don't have very good angle control, but they apparently have very good samples. They just make the best sample they can, and then they look at what angle they have. So that is not very reproducible in terms of angles. But the other groups, they really try to target an angle, but maybe there is some disorder in the angle. So there are these two complementary things. But at least this Barcelona group, a lot of the, for example, charge neutrality being the strongest insulating state. This was something that was very puzzling before. Why was that not insulating? That seems to be the case. So that seems like it's reasonable. Maybe they do have better samples.
Yeah, I have a question. Ashvin. Yeah. So this, how much of this gap is controlled by this AB sublattice breaking? Because in the Chern insulator, that's how you first separate it out, right? And second thing is what happens to the other filling, like quarter filling? And
that's a good question. They don't see it at quarter filling. Yeah, it's only seen at this 3/4 filling, and I don't know why. That's a good question. Maybe there's more band overlap there. The gaps, I think the gaps here are like 3 millivolts or something. But the HPN splitting gap is like 30 millivolts. This is much smaller. So this is presumably the gap to the exchange gap, not the HPN splitting gap.
As you mentioned that in the BM model, the W1 and W2, W0 are exactly equal, and you still get the flat band at least at the first magic angle.
Right.
At least like order of magnitude flat band. So it seems like the symmetry that you started with, the chiral symmetry, is not actually important for getting the flat band. Is there a physical way to understand that why it can be that a symmetry which is so important in your model showing that there's flat band but is not in BM model?
Maybe another way to say it is, this physics it's actually quite resistant to changing W0. Okay, the band gap to the next band closes, but it takes a really long time, compared to the next one. And we don't quite understand that. It's some property of this first magic angle wave functions that they are quite resistant to tuning this AA hopping. We don't have a good explanation for that.
So in case of when you put the SBN on this twisted bilayer graphene sample or whatever, so will it matter that the SBN is commensurate or incommensurate to any of the layer?
So whether the Moire lattice is commensurate with the graphene lattice?
Yes.
So probably not, because it's such a small angle.
Okay.
So if you think about it, what you want to know is if I give you a scattering of order the Moire reciprocal lattice vector, if you make multiple scatterings like that, you may end up getting the atomic reciprocal lattice vector.
Okay.
If it's commensurate, you can do that. But that requires, like order of 100 scatterings. Right?
One question more means where people usually talk about that correlated insulator or the Mortis insulator. Why means there is a possibility that at such a long high interaction, the electron crystallize and form the Wigner crystal?
Yeah. I'm not sure how to think about that. I mean, it is a problem of interacting electrons in some periodic potential. Wigner crystal is like you forget about the periodic potential.
Okay.
You solve the problem without the periodic potential first, and then you put on the potential to lock the Wigner crystal.
Okay.
But here you're talking about some Dirac problem. It's not very clear to me how you do that first step cleanly, right? You don't want to have this hopping between layers. But Dirac electrons, can you actually form a Wigner crystal? Is not obvious to me. If you had a quadratic band, maybe that's a good starting point. That think of interactions giving you a Wigner crystal, and then you help it with the periodic potential. But I'm not very sure how to do it here.
No, absolutely flat. There is no kinetic.
I mean, as soon as you say a band, it means you put in a periodic potential. Right? I think you want to start with some continuum limit where you don't see the potential at all, get a crystal, and then lock it.
Are the fractional Chiral insulator or the fractional quantum Hall states that you see with these Landau states the same as what you expect for a Chiral insulator or a quantum Hall?
Yeah, pretty much. With some, the exact wave functions are different, but yeah, like, fractional charge, all of that.
Yeah, I have a question concerning actually the gap exactly at half filling. And as you said, actually, you see it experimentally on the samples where the back gate is closest, where a priori we expect the interactions to be the weakest. Is there a simple explanation on why actually you see it in this?
Okay, maybe there are two things going on. Yeah, that's a good question. So yeah, so in all of these cases, you see the charge neutrality state being gapped. But it's actually true that if you look at the value of the gap, it's going down. So it's kind of sensible that the interactions are weaker. But this is probably not the reason why you have a gap here and not in the Pablo samples. So the fact that you don't have a gap here and you have a gap there, I don't think it's because the gate is closer. Something else. Maybe there's some, we think it's kind of some sort of strain on the sample. So you break the rotation symmetry by applying some strain. And that turns out to be very good at closing the gap. Although why it closes charge neutrality and not these other gaps, that's not very clear.
More questions?
Question.
The one with the gates. No. So there are 3 different distances. Angles, even the angles are different. So are those the magic angles for that respect?
Yeah, that's a good point. Yeah, I don't know. Yeah, it could be, you're saying it could be because the angle is different.
Yeah. The thing is, so like, are these the only 3 data points which we have, or are there?
There are others like the other groups have done with a thicker HPN gate. So there are ones with much thicker HPN gates.
No, just the variance of the gates of the gate.
Right. The distance of the gate is the HPN thickness.
Oh, because you see the middle, call it the brown layer. If you just look at the middle, the brown layer.
This one, you're talking about?
Yeah. So does the thickness it certainly varies with the gate distances? Is there a discernible pattern in there?
Yeah, so you can make it a bit more quantitative. You can extract a gap from this.
Also, the superconductivity patterns are also very different.
Oh yeah, superconductor is completely different. Yeah, but this I think you can extract a pattern because you can extract a gap and it goes down.
Not going down, that's...
Well, I don't know from this whether you can see it. You look at the temperature dependence of the resistivity and fit that to an exponential.
More questions?
Yeah, let's talk later.
Just have a short question. Is there any experimental reason to think that all these correlated insulators are same or different in nature? These correlated insulators?
Yeah, I think Erez will talk about this experiment where it looks like different populations are being gapped successively. So it may suggest you have the same correlated insulator, but maybe with different, like one case spin polarized, other case is spin singlet, maybe, but ultimately the same. It's not a priori, very little is known. And a lot of things are, yeah, the response to magnetic fields can be quite different for the different insulators.
Okay, let's thank Ashwin once more.